Hello, this is Bob Walkup, and I'll be speaking today about best practices for HPC workloads on public cloud platforms. My colleagues and I are from IBM's research division, so our examples will be from IBM Cloud, but many of the considerations apply to other cloud platforms as well. I'll discuss the building blocks that you'll use to construct an HPC cluster, talk about communication, tuning parameters for TCP protocol, which is popular on cloud platforms, what to do about hyperthreading, and I'll show some application scaling examples. When you go to a cloud provider, you'll need to choose the building blocks to construct your HPC cluster. And there are many options to choose from with varying amounts of memory, cores, network, and storage. On IBM Cloud, the virtual machines are built on Intel servers. There are 2 virtual CPUs per core, and there are families of virtual machines with 4 GB of memory per core, 8 and 16 GB of memory per core. You can get virtual machines with as few as 2 virtual CPUs or as many as 128 virtual CPUs or 64 cores and up to a terabyte of memory. So a wide range of choices. And my first recommendation is that if you have an HPC workload that can fit on a single virtual machine, again, up to 64 cores and a terabyte of memory, then choose that option. And the reason is that you'll have shared memory communication, which is very efficient. That's shown in the next chart. This is a plot of the exchange time for messages using MPI, comparing shared memory with Ethernet. Shared memory lowers the latency by about a factor of 100 compared to Ethernet communication, and the bandwidth is about 10x better with shared memory compared to Ethernet. So overall communication performance is really good with shared memory communication, and it's much more efficient than Ethernet. And so if you have a communication intensive job on cloud, if it can fit in a large single virtual machine, definitely go that route because you'll get very good parallel efficiency and excellent communication performance. When you have to scale out to many more cores, you need to understand how network bandwidth is allocated. And this table is for IBM Cloud. Going across the columns, we have virtual machines with 16 virtual CPUs, 32 and 48 virtual CPUs. And the table indicates that the aggregate network bandwidth that's available increases with the number of virtual CPUs. But the important thing to recognize is this row. If you have just one virtual network interface, in other words, one Ethernet interface per VM, that interface is capped at 25 gigabits per second. So that's the effective network bandwidth limit, not the aggregate one that you see up here, but the per network interface bandwidth. And so if you only have one interface configured, your best network bandwidth per core is going to be with the smaller VMs. This guides the selection of virtual machines when you need to scale out. Um, you can create additional interfaces, and I'll show you an example of that, but the same consideration applies. There is a cap on the speed per virtual network interface, and it's just awkward to deal with multiple network interfaces. So most commonly, you'll have just one, and that will drive you to choose these relatively smaller virtual machines as your basic building block. Um, this chart shows TCP tuning options. I won't go into detail. I'll mention that these tuning options really should be applied to every virtual machine when you're using TCP for communication. And these recommendations come from the Open MPI frequently asked questions. Some of them come from the Mellanox performance tuning guides. And I recommend just applying these options whenever you're using TCP for communication on cloud systems. The chart on the right shows an example of using just one network interface where you can max out the exchange bandwidth at large messages shown in this plateau, or you can use 2 network interfaces and double the bandwidth. When you use 2 network interfaces, you could stripe messages shown in brown, or you could use a different strategy where some of the ranks use one network interface and other ranks use a different network interface. And that gives you better performance at intermediate messages. You can achieve this strategy by suitably setting UCX net devices and use MPI built on top of UCX. This mechanism becomes available to you and it's very effective at being able to exploit multiple interfaces. What to do about hyperthreading? Um, Bottom line is that if you're scaling out and you're using TCP protocol, your best strategy is going to be to bind a single processor thread per core and leave half the virtual CPUs free. And the reason for doing that is that TCP communication is very CPU intensive. It requires kernel threads to complete the messaging, and those kernel threads need slots for execution. Our experience has been that you get dramatic slowdowns when you try to use all the hyperthreads, all the virtual CPUs for computation. It can slow your code down by up to 10x or more. So it's much better to just bind one process or thread per core and leave virtual CPUs free. Um, and I'll just show a few examples of case studies. The first one is OpenFOAM, a motorbike tutorial, where I'm going to compare the performance that you see with a single virtual machine using shared memory. That's this column, compared to using 4 virtual machines that are Ethernet connected. The same total number of virtual CPUs, 128 virtual CPUs, 64 cores in both cases. And you can see that the elapsed time is significantly lower in using shared memory for communication. Um, in terms of cost, these cost about the same per unit time. Takes a lot fewer seconds to complete a job with shared memory communication. So this is the cost-effective and time-effective choice. So when your application can fit in shared memory, make that choice. When you have to scale out, you can have really good success on current cloud systems, even with the Ethernet and the long latency and all that. This shows some examples. The first one is Warf. It's weather research and forecasting model, a high resolution continental U.S. grid, 2.5 kilometer resolution. Here are the grid dimensions. There's only one TCP network interface per virtual machine. I am using virtual machines with 16 virtual CPUs. That gives me the good network bandwidth per core. And what you see is good scaling and good performance, better performance per core on IBM Cloud than on the Summit supercomputing system. And what you want to achieve in a weather forecast is a high simulation speed. A simulation speed of 50 means that you can simulate 50 forecast hours in one wall clock hour. That's a very attractive range to be in for production weather forecasting. And the TCP Ethernet networking on current cloud systems is more than adequate to get you there, as long as you choose your virtual machines suitably. Next example is a Boltzmann transport equation. This is one of the commodity technology system benchmarks from US Department of Energy. And again, it's very network intensive. The local domain for this benchmark is only 4x4 grid cells. So the surface area to volume ratio is really high, and this benchmark is very network bandwidth intensive. But it's not very sensitive to network latency because message sizes are about 100 kilobytes. And what we see is on cloud, scaling is excellent, performance per core is very large, and that's because this application benefits from SIMD instructions on Intel processors that gives you the better per core performance on cloud compared to Power 9. And I'll stop there with a brief summary. When you're doing HPC on clouds, you want to be very careful about choosing the building blocks, your virtual machine instance types. Definitely go with a single large VM when your workload can fit. And when you're scaling out, do use the TCP tuning options. Be mindful of bandwidth limitations per network interface. Bind one process or thread per core. Leave virtual CPUs free. You need to do that so that TCP communication can be effective. And keep in mind that TCP is best suited for applications that are not very sensitive to messaging latency, but they can be very network bandwidth intensive. So thank you for your attention.